All right, we gotta learn and talk about this funnel problem right here. Now, there's some things I want to talk especially about on part B, but letter A, see how easy this is right here. It gives us an equation for the radius, and then says find the average value of the radius of the funnel. Now, average value, that's just your average value formula. That's what I'm using right there. So I'm going to integrate in between 0 and 10, that function right there. Now, no calculator, pull out the 1 over 20, easy integral though. So plug in the 10, plug in the 0, and then just be a little bit careful. And you could stop right here. You don't have to reduce the fraction. If you have some large fractions here, just leave those alone. That's it, right? It didn't ask for units on this one, but anytime you use the average value, the units always kind of stay the same. It's just what that average radius is going to be right there. So easy integral, easy formula. Just be a little bit careful with your numbers and stuff at the end. Now, I remember the year after students took this test, they popped out there a couple days later and they're just like, hey, Mr. McGee, how the heck do you find the volume of a funnel? What's the formula to find the volume of a funnel? There is no formula to find the volume of a funnel, right? When we did our volume stuff a long time ago, we said, hey, we're going to take this curve, we're going to spin it around the x-axis, we're going to spin around the y equals 4. What shape do you see there? Some of us saw a donut, some of us saw a butt cake thing, some of us saw like a hand, we saw like dishes and sculptures and all kinds of stuff that we saw, but we never said how do you find the volume of that thing that you're seeing right there, right? So we didn't care. We knew we were going to use the disk method and the shell method and the cross-section method to find the volume of whatever shape that it is. So it doesn't matter that's a weird shape they're throwing at us. I remember it was funny this year. The internet had so many jokes about the AP test there. One I'm remembering, it was like a margarita glass, something like this. Like find the volume of this. This is what I need to have after that AP test and stuff there. Duh. But anyways, but that's like no kidding. Like you don't need to know the volume of a funnel. That's what your disk and shell and cross section methods do. It finds the volume of whatever shape that we want there. Now, most of my students said that they did some normal stuff and that I think they were just fine there. But if you get to something weird on the AP test, just try something that we've always done before. Most likely that's what it is that you were meant to do. There are two ways that you could approach this problem that we've done before, we've done a lot of before, that you could all handle getting this thing right. One way, it says, when you read the problem, it says circular cross sections, right? So circular cross sections, since I saw the word cross section, I thought, let me find this volume using my cross section method. Okay, and if you don't like that, I'll show you another method you could use as well. But cross sections and circles, remember for the cross section method, you integrate the area of your cross section shape. So I'm going to integrate pi r squared. They give me the r, so I'm going to integrate pi times this r squared. So I squared that. That's where the 1 over 400 came from. I squared that in between 0 and 10. And then easy integral, but you just got to do a little bit of algebra first, multiply that stuff out, integrate it, plug in the numbers, and then I didn't have a calculator on this one, but notice I could factor out a 10, and then that made the numbers a little bit smaller to work with right there, and then you just kind of simplify that. So it turned it into a pretty simple integral there. And it was a volume. It didn't ask for units there, so I didn't have to worry about it, but I just want to stress again, just in case we need them, that's cubic inches for the volume. Make sure you carry down the pi there. Now, if you don't like that cross-section method, look up here. I got another way. You could just use your disk method. If you look at this shape, I was staring at this long enough where I saw, okay, if this is the curve here, and I took this curve and I spun it around that y-axis, it creates this three-dimensional funnel right there. So I said, okay, let me just put my y-axis straight down the middle right here. And if the equation of this curve, this is the radius of one of those circles right there. See how that circle's right there? Boom, there's your radius. That's halfway across. That's the distance from that y-axis over. Is anytime we measure from the y-axis over, that's always x. And that's also the half of that circle, which is the radius of that circle right there. So that's why I jotted down. When they gave me the radius, I jotted down for myself that also means that's my x. My x is that same thing as the radius. And then so I can use my disk method on this problem as well. I could draw everything's in terms of y's here. So I want to draw my rectangle this way to make that little part vertical to be a dy problem. And so your capital R will be the distance from your axis of revolution to your farther edge. When you measure from the y-axis over, that's always x, but it's a dy problem, so that's why you put in the equation what it's equal to. And then your little r is the distance from your axis of revolution to your closer edge, which is the one and the same. So little r is equal to 0. And then if you do your disk method, you got your pi guy out in front, you got your capital R squared minus your little r squared. And notice that this integral right here is the same exact thing as this integral right here. Just this has h's in it. this has y's in it, but either way you integrate it, you're going to get the same exact number right there. So when something looks weird, you're supposed to be doing your normal stuff there, okay? But that's the whole point. That's what calculus allows us to do, is find the volume, whatever shape that you want. You don't need to freak out because you got a funnel and you never seen a funnel before in your life. It doesn't matter. Like, you can still find the volume, whatever shape, whether you see it or not, just what those normal methods will do for us right there. So half the battle on the test is just, believing that it's going to be something that you can handle, and we're going to be just fine. And just do the best you can. Just try normal stuff there, we'll be good. All right, now letter C is like a related rate problem, because it says the instant when the height of the liquid is h is 3, the radius is decreasing at a rate. And so I said, okay, the radius is decreasing. That means that's my dr/dt. And then it says at this instant, find the rate of change of the height. So they want me to find the dh/dt when that h is equal to 3 right there. So the only equation we had here was the radius equation, which is perfect because I needed the r's in there to get the dr/dt involved, and I needed the h's in there, and I have r's and h's. So I started with that radius equation they gave us, and I'm just going to take the derivative with respect to time. So the derivative of r with respect to time is your dr/dt. The 1 over 20 is just a constant that I can carry down. Derivative, the inside is just going to be a 2h, but we just did derivative. We just did the derivative of h's with respect to time, so you got to tag on the dh/dt, and then you can simplify that a little bit, and then just plug in the 3 for the h, solve that for the dh/dt, and that's how fast that height is changing at when the h is 3 inches right there. Iced coffee.